Welcome back, everybody. We're talking in this section about a branch of chemistry that is very different than any other branch that we'll study this year, but it's an important branch of chemistry, and it's one that fits nicely as we talk about kind of the inner workings of the atom. We've learned about the nucleus, and we've learned about protons and neutrons and electrons. And so discussing nuclear chemistry, which is a discussion of what happens within the nuclei of atoms, is really important at this time, and I think fits nicely. Radioactive decay are processes that take place within unstable nuclei that changes them in very drastic ways and often produce a lot of energy. And so, as I mentioned, this is very different chemistry than we usually will talk about, because what you see within nuclear reactions and radioactive decay, we see individual isotopes turn into different isotopes and different elements, and that is not typical or even possible under the guise of a traditional chemical reaction. It doesn't mean that it's necessarily difficult, though. And so I think where I want to start today is just a brief look at what a nuclear equation looks like and how it's different than your typical chemical equation. In a nuclear equation, instead of talking about products and reactants, we usually will discuss parent and daughter isotopes. And on the left side of this arrow, in the middle of the nuclear equation, on the left side, we have what's known as a parent isotope. And for radioactive decay, these parent isotopes are usually very unstable. Okay, so we have an unstable parent isotope, and there are a number of reasons that a nucleus might be unstable. And this is something we're going to discuss in detail in a later video. But the process of decay means that some particle or some form of energy is released as the parent isotope decays into what's called a daughter isotope. And that daughter isotope, without fail, is always going to be at least more stable, if not completely stable, compared to the parent isotope. The nice thing about keeping up with daughter and parent isotopes is within a nuclear equation is that the numbers that we associate with individual isotopes, like the atomic number and the mass number, have to stay equal or balanced on the left side and the right side of the equation. So if I look at the parent isotope in this particular case, I have iodine. It has a total of what we call 131 nucleons, 53 protons. We can tell that by looking at the atomic number. And it has 78 neutrons, which we can get from finding the difference between the mass number and the atomic number. On the right side of the arrow, we have our daughter nuclei and another particle, in this case, an electron. And what we see in this particular case on the right side is that we have a daughter with an extra proton, but the mass number hasn't changed at all. And in total, the right side has to balance out with the left. And so what you'll see is something like this. While the daughter isotope has an extra proton, we balance that with an ejected electron, which we're going to come to know as a beta particle. And electrons, which we note have a negative charge and very little mass, we write the negative charge in the same place that you would usually write the atomic number for an isotope, because electrons are essentially massless or very, very close to massless compared to protons and neutrons, we give them a mass number of 0. So think of it this way. On the left side, I have an atomic number of 53 and a mass number of 131. On the right side, if I put 54 and -1 together, I have 53. If I put 131 and 0 together, I have 131. So there has to be balance between the right side and the left side. And that's how you're going to know if you're doing things right when you're trying to balance a nuclear equation. There are really three types of radioactive decay that we're going to look at in detail. We're going to look at what's called alpha decay, where a big chunk of the nucleus is ejected from the nucleus. We're going to look at two types of beta decay, where we look at particles like electrons and positrons. And we're going to see a type of radiation known as gamma radiation, which is released in a lot of these processes, which produce enormous amounts of energy. So a radioactive nucleus is one that is going to change because it's unstable and emit some form of radiation, whether that be a particle or energy of some type. Let's look a little closer at these three types of um, forms of radiation that are often released. What I've shown in this diagram is beta particles, alpha particles, and gamma rays being ejected from a nucleus and passing between two charged plates. And the first thing that I notice is that the beta particles are really attracted to the positive plate. And what that means is the beta particles are negative in charge, and the alpha particles down here are attracted to the negative plate or deflected by the negative plate. That must mean alpha particles are positively charged, while gamma rays pass straight through, which means they must be essentially neutral. They don't have a charge. The other thing I notice with the alpha and beta is the ways in which they are deflected is substantially different. The beta particles seem to really strongly be deflected by the positive plate. And that tells me beta particles are probably light. Their mass is probably very low. Whereas it seems like the alpha particles are just barely um, uh, deflected from the negative plate, and that tells me that those alpha particles must be much more heavy or have a greater mass. So in our next video, what we're going to end up doing is looking in detail at these three different types of decay, but we're going to save that until our next video. See you then.